Hello everyone, welcome back. Um, Hope everyone is doing well. Now I believe that this coming exam will be the last leg in your final exam, um, which will be your further statistics. I think. All right. Now I try to provide uh, one or two more sets of past year paper for your revisions. Hopefully, it will be useful for your final exam. Right now, today I'm going to provide a full explanations on further statistics, November 2020, paper 43. Right, you can check out. You can check out the description down here. Right, let's get going. Right, welcome back. Let's look at the first question here. We have Kayla is investigating the length of leaves of a certain type of tree found in two forests X and Y. Okay. Now, before we proceed further, in this question here, they are actually referring to two forests X and Y. So in this case, I would say naturally we will assume that the population's variance or standard deviations will not be the same. All right. So that's our assumption. All right. Now she chooses a random sample of 40 leaves of this type from forest X, and then after that she record their length as X centimeter. Now she also record the length of Y centimeter for a random sample of 60 leaves of these types from forest Y. Now her result are been summarized as follow in the form of summation. You can see that sum of X, sum of sample X, sum of the square of sample X, sum of Y, and then finally you have sum of square of y. Okay, now find a 90% confidence interval for the difference between the population mean length of leaves in the forest X and Y. So whenever we deal with difference between the population mean, in this case, generally in the exam, we always look for two conditions. The first one is whether is there's a possibility in the statement that indicate that both their population variance are the same. If not, usually we assume that the population for forest X and Y would not be equal to each other. Now that would be our assumption, right? So that will be the one that we're going to use here. So we assume that both the variance for forest X and forest Y are not equal to each other. Okay. Now for that, we are going to use certain sets of formula based on our assumption. All right. So I'm going to write down the assumption here. So assumption is population X and Y um, does not um, have equal standard deviation, equal variance or equal standard deviation. So here I'll write down equal variance or standard deviation. All right. So once you have made up your mind regarding the assumptions, now we're going to start to use the sets of formula based on our assumptions here, right? Now, before we can actually go ahead and calculate the confidence interval, now we need to set up a few parameters before we can proceed. Okay, so I'm going to write down the setup stage here. So what do we need here would be, of course, the mean for sample x. Here, sample mean for sample x. We're going to write down here, which is given as sum of x divided by the sample size in this case, right? So I'm going to write down the sample size x as 40 here, just as a reminder, whereby the sample y as 60 here. All right. So this one I will have to divide by x. Okay, based on the numbers there, I would have this divided by 40. Okay. Okay. Now, if you use your calculator to tabulate this, you would end up with 6.05. All right, I have already pre-calculated here just to save time. And then next, we're going to proceed on with the same calculations for sample mean for the sample collected from forest Y. Now I'm going to drop the formality of writing the summations formula. Here I just write down 373.2 divided by 60 here. All right, so I have already pre-calculated this. All right, so if you tabulate this, you would get 6.22. All right, okay. And then next, we also need to obtain the estimate for the population variance. So the estimate for the population's variance. Now in this case, the first one. All right. Now we're going to use the unbiased variance, sample variance in this case. Now the formula is given as here. There are many versions of this formula. Now, if you want to make use of all this, you can actually use this formula here. Which can be found in your data booklet MF19. Right. So from here itself, we are going to substitute in 242.0, subtract off with 1587.0. Oops, I think I copied the wrong number here. I think I forgot to enter 2 here is a square in this case, right? So because of that, I'm going to key this one in as 17.0 and then subtract off with the square of this. Okay. And then you can actually go ahead and calculate this. I have already pre-calculated this just to save time. You would have 3 point, I need to refer to my calculator here, 15128, right? So if you leave it to 5 decimal places in this case, right? And then we're going to repeat the same procedure here to obtain the unbiased sample variance for samples collected from forest Y. Using the same sets of formula. Okay, now in this case where I'm going to key in the different value 32.6 here, and then that will be 373.2 divided by 60. Okay, again I have already pre-calculated this. It should be 3.581 129. All right, so we pretty much has already completed the setup stage. Now we are going to look at the formula that we're going to use for 90% confident intervals here, right? Okay, yeah, there's one more step that I forgot to mention here. Once we have obtained the sample variance, we need another um, parameter which is called the standard of error. Usually textbook they don't really stress these parameters with the proper notation, but I would like to stress it here. The calculations that I'm going to perform now is called the standard of error. I just write it down here. Standard of error, which is labeled as this. Usually is labeled as this. Standard of errors, sorry. Standard of errors, I shouldn't be using a square here unless I would say variance or errors, but that would sound a bit weird. So therefore, um, the standard of error usually is labeled as this, which is the because we make assumptions that the population does not have the same variance in this case. So therefore, we are going to use this formula here. Okay. Now in this case, we're going to use our estimated unbiased sample variance for these calculations. So therefore, this one here, sigma 1 will be this one here. Okay, I'll just write it down here for reference. So sigma 1 should refer to this, sigma 2 refer to this one here. Okay, so from here, I can just substitute this value into here. All right, and then once you calculate this, right, I have already sort of got an answer for this. Okay, that would be 0.13847 square root. Okay, right. So if you key into your calculator itself, you would be able to obtain a certain value here, right? But I'm going to leave it at this point. Later we're going to use this in our next calculations there. Right? Okay, so at this point, this is the most important section. I'd like to stress again the assumption. Next would be the setup stage. You get all the parameters that you need. All right. Now, next, I'm going to pause here for a while. I'm going to move on to the objective of the question, which we are going to answer as finding the 90% confidence intervals. What will be the formula that we're going to use to find the 90% confidence intervals for the difference between the population mean, lengths of leaf between the sample collected from forest X and Y, right? Okay, now let me clean up the part that we don't really need at this point. But I'm going to write down all these detail down. So first of all, I need my mean in this case, of course. So I'm going to write it down here. Oops, sorry, I mentioned my mean. Okay, so I need my mean here. I'm going to write down my mean will be somewhere here. That will be 6.05, and then at the same time I will need my uh, standard error in this case. Oops, standard errors. Okay, I think because this is a standard errors between the difference, right? In order not to confuse use, maybe it's best to write down as x bar minus y bar, just to show that it is the standard errors that we encapsulate to represent the difference between the population mean here, right? So therefore, the standard or errors here is given by 0.13847. Okay, I just keep it as a square root first. All right, now the rest we don't really need at this point of time. Okay, so I'm going to erase the rest, and then we're going to answer that very questions here. Okay, all right. Okay, confident intervals. Here I just put a short form here, confident interval. 90% confident intervals here. Uh, Now, the formula for finding confident interval is given as such. For difference between the mean of population is given as this z score, and then at the same time we have the standards of errors here, right? It's always the difference. This part will be the difference, and then the z-score here, and then plus the standard or error. I just write it down in short form there, right? Now in this case, we are going to use a z-score, or a normal distributions, z in this case. Some of you might be wondering, okay, now based on all the lessons that you have done in statistics, okay, now usually if the if the population variance is not given or is not known, usually we prefer to use a t distribution, or student t distribution in this case. So therefore, why would I use a z score or z normal distributions here, right? Now the main reason is because of central limit theorem. Now central limit theorem state that we can assume that the distribution is normally distributed if the sample size for each one of them has already exceeded. I would say if you want to be strict, it will be exceeded um, 50, but according to the textbook reference, as long as the sample size exceeded 30, we can assume that the population is normally distributed. Therefore, we can actually make use of normal distributions. In this case, the normalized or standardized normal distribution Z. All right. So I hope you are clear on this. This is more like the estimations, okay, and then based on the assumption that we have made. Right. So from here itself, we are going to substitute all the parameters that we have already captured just now. So we have 6.05. And then, oops, this is the part that I forgot to write down. The mean is 6.22 just now. Right. So I'm going to subtract off that. Okay. Now, bear in mind, some of you might be um, interested to know, must I always write x bar minus y bar, like the difference where I'm going to take the sample mean of x subtract off the sample mean of y, or could it be the other way around? Yeah, of course it could be the other way around, because they just mentioned the difference. They didn't say that which one should subtract which. So therefore, you could have, or we can also write down as such. Okay, so both can be accepted, right? And then here you have plus or minus z-score. All right, now z-score is important. 10% confident intervals. All right, now need to draw a diagram here, just to give you an idea what are we looking at, right? So 90% confidence intervals, it means that this part is the confidence intervals. Um, Ranging from Z, usually we prefer to write down like this. Okay. The alpha is a significant level, right? It's divided by 2 because both side is actually half of alpha in this case, right? Okay. And then the confidence interval is given here. This is 90% confidence intervals. But the curious thing about your MF19 is your MF19 does not give you this shaded region directly, but instead the MF19 would actually give us this area. Therefore, we have to make use of this area. We know that this is 90%, and then because it's symmetrical, therefore the blue shaded region would be 95%. All right, would be 95%, and then that would be the value that we are going to use to look for the standardized z-score. All right. Okay. Now I'm going to show you the MF19 now. Hopefully, okay. Here we are. So this is the MF19. Under normal distributions, we are supposed to look for 95%. Bear in mind, this is the common mistake done in the exam. It should be 95%, not 90%. All right, because that's how your data booklet is being designed. Next time when you go to university and so on, you are using a different data booklet, then please read the instructions, which area that they are referring to. Right? So here I'm supposed to look for 95%. Okay, so 95%. So 95% should be somewhere here. If you look properly, this is 1.6. Okay, let me label that properly. This is 1.6. Okay, 1.6, 1, 2, 3, 4. 1.64, and then you can actually add another 5 here. You can add a 5 here to make it 0.95, which is 95%. And then this 5 is actually referring to the number 5 on top. So therefore, this z-score is 1.645 actually. So this is 1.6, this is 4, this is 5 here. All right. Now that's how we obtain the z-score. After that, we're going to multiply that with our standard of error, which is given as such 0.13847 square root. Okay. And then from here onwards, we will be ready to tabulate the confidence intervals, 90% confidence intervals here, right? So if I were to tabulate this, I should be able to get, in this case, I will be able to get a negative. You can see that this is a negative 0.17. Negative 0.17, and then after that I will have 645 square root here. All right. And then of course you can key in all this into your calculator. For the negative part, all right, for the negative part, if you choose the negative, you would end up with, I have already calculated this, so therefore the negative part will be negative 0.7, sorry, negative 4. Is it negative 4, 4? Let me see, is it, oh sorry, negative 0.7. I always look at the wrong number here. Yep, okay. So you will get a negative 0.782 for the negative part, and then for the positive you will get 0.442. Yep. So therefore, this is one of your confidence interval. So here I'm using a square bracket because you can either write in the interval form using the square bracket form, or you could have written down this as such. Or you can write down in this notation. So it's either this one or this one here. Both represent the same result here, right? Okay. Now next, as I mentioned before, instead of having x minus y, you could have a y minus x instead. Right. Now, if you have chosen y minus x, then therefore your value would not differ too much here. So if we refer to this part here, that does not refer too much from here. What we have is 6.22 minus 6.05 here, plus or minus 1.645, and then multiply by 0.13847. And then from here itself, this is 0.17. Okay, and then from here, if you finish off this, you will get negative 0.442, and then the other part will be 0.782 inclusive. So don't forget that. Right. So these are the two sets of possible confidence intervals that represent the difference between the two population mean here. Right. So I hope you are clear on the first question here. Right. Now I'm going to move on to the second question shortly. All right. Next, let's look at another sample past year paper, which is not actually the November series here, but I sort of want you to be able to compare similar format of questions related to question one that we did just now. Right? So you can see that here, the storyline is a little bit different now. The annual salaries of workers at the two factories A and B are to be compared. Right now, the salaries in tens of thousands of dollars at A and B are denoted by X and Y respectively. For a random sample of 40 workers in factory A and a random sample of 50 workers in factory B, the result are as follow. All right, now you can see that they give us the information in terms of its summation. These are all the data for the sample collected. Now the population mean salaries for A and B been denoted as mu A and mu B respectively. So you can see it here. All right. Now the population variance for salaries at A and B cannot be assumed to be equal. Right now, for this question is clearer. At least they told us that the variance of the populations are not the same. Right? So here we are going to test at the 1% significant level whether the mean populations of B is greater than the mean populations of A or not. Okay, so the first step is to write down the statements for the hypothesis here. Right. Okay. Now, that just reminded me of questions raised by students when they look through my videos, right? So, how do we actually identify the alternative hypothesis? Okay, the easiest way in the exam would be the population variance of salary at A and B cannot be the same. Okay, that one is cool. Right. Now, what we want to test now would be test at 1% significant level whether the population B is greater than populations A or not. Now, this test here would actually give us an indications about its alternative hypothesis. So this one will give us the alternative hypothesis, right? So we're going to write down, if you're not sure about your null hypothesis, you can write down your alternative hypothesis. So your alternative hypothesis state that we want to check whether um, the mean populations between A and B, between B is greater than A or not, all right? You can either write down like this, is greater than, okay, whether it's greater than A, you can write down like this, 0, okay, or you can also write down like this, is greater than mu A in this case. Both of them refer to the same result here, right? And then usually for null hypothesis, right? For null hypothesis, since we are testing a one-tailed test in this case, we are trying to check whether the mean B is greater than the mean populations A in this case. So most probably our null hypothesis, usually I would say would be, you can either write it down like this, equal to 0, or you can write down like this, is equal to mu A. Okay, both also can be accepted, right? All right, now I hope that is clear on how to describe the hypothesis statements, right? Now, once you are satisfied with this, okay, and then knowing the assumptions that has already been given to us, we are going to finish up the setup stage. Yeah, always go to the setup stage, whereby we need to find the mean. Okay, so here I'm going to write it down. So we need to find the mean here. So that will be 256 divided by this one is 40. There's a sample size of 40. The second one is 50. All right. So for this, I will need to divide by 40 then. All right. And then for that, you will be able to, I have already pre-calculated this so that I can refer it very quickly. Now in this case, you will get, let me see, it should be 7. Is it 7? Let me see. Oops, no, it's not 7. Divided by 40 should be a 6. Yeah. So this one should be 6.4. Okay, 6.4. And then you can also calculate the y. Okay. In this case, it will be, what do we have here? We will have 382.9 divided by 50. Okay, so from here you will get 7.658. 7.658, yeah. Okay, and then next, as usual, you need to calculate the unbiased sample variance. So here, I'll write this one down as this. Okay, and then as usual, you're going to follow the same formula here. So here I'm not going to write the formula, but instead I'm going to write down the numbers here. Divided by 39. Okay, so if we calculate this, right, we would end up with, let me see whether I got that correct or not. Hold on, just let me check my answer again. That would be 4039. So therefore, I should end up with 6.985. Okay, that's what you will get if you key into your calculator. And then the same go for the unbiased variance Y, or for population B in this case. Now the same thing is 3148.8 divided by 50, and then 49 here. Right, now for this we will get let me see, that will be 4.419. If you key into your calculator, you will get this number here, right? So I hope that is clear. And then since they have already given the assumptions to us, all you need to do is just calculate the standard of error. Here I'm going to write down the standard of error would be given as 6.985 over 40. Okay, square root that, right? So in this case, I would get, let me see, I would get 0.513 after you square root that, right? Okay, right. Now that's what we have at this point of time, right? Now I hope that is clear. Now next, the most important stage is the next stage, right? So the next stage, I'm going to write it down all over this side, which is the test statistics. Right. Now, test statistics is very important, where we're going to compare our sample test statistics. Okay, so our test statistics is given by, we're going to take the difference between here. Since we are testing the alternative hypothesis as population B subtract population A, therefore this one would be, we're going to take Y minus X divided by standards of errors here. Okay, that's how it look like. And then in this case, we will get 7.658 subtract out with 6.4 divided by 0.513. Right. So 513 or 5128 if you want. Right. So here I just write down another one in case some of you have more significant figures. So here you can also use 28 here. Right. Once you tabulate this, you should get, let me check my answer. You should get, let me see, you should get 2.45. Yeah, correct. You get 2.45. Right. Okay. Now I hope that is clear at this point of time. Now next, we're going to compare this test statistics with the critical value from the MF19 now. Right. Alright, now I'm going to pause for a while for you to check all this value before we start to compare the critical value. Right. Okay, yeah. Right. So I'm going to erase off the sections that we don't really need at this point of time. Okay. So we don't need this anymore. Okay, let me clean this up for a while. Okay, cool. All right. Now next we're going to refer to the MF19. Bear in mind this is a 1% significant level. So 1% significant level is a one-tail test. So therefore I'm going to draw the diagram here. Oops, sorry about that. Okay, so it's a one-tail test, 1% significant level is on the right-hand tail. So this is a 1% here. So this part here is 1%. Right, that part is 1%. And then your data booklet will give you this shaded region, which is 99%. So when you refer to your data booklet shortly, you're going to look for 99%. Okay, let me see whether I got my data. Okay, I'm going to shift it over a bit here. Okay, hold on. All right. Okay, if you refer to your data booklet here, right, we are supposed to look for 99%, 99% shaded region. So therefore, 99% would be somewhere here. Right. Now you can see 99%. So this is 99%, very close to 99%. Right. Therefore, the z-score would be 2.3. This one will be 2.32 here. This is 2.32, and then we need to add up two more. So if we add up two more, I need to scroll to the back. You can see that if you add up two here, it will give you 0.99. Okay, so therefore this is 1, 2, 3, 4, 5, 6, 6. So that's a 6. Therefore, the z-score for this would be the critical. So in this case, I just write down C critical, or the critical z-score based on the MF19 is given by 2.326, which is here. All right, so I hope that is clear. And then now next, I'm going to remove this. All right, okay. So now we have our test statistics, we have our critical value. We're going to make a conclusions based on this. Okay, now we are going to make a conclusions whether we are going to accept or whether we're going to reject the null hypothesis here, right? And now as you can see, 2.45, 2.326 is here, and then this region is known as the rejection region. Now we want to see whether our test statistics actually fall in that region. Now sadly here, the 2.45 is found in the rejection region itself. Therefore, we are going to make a decisions to reject. Firstly, we're going to say that we're going to reject H naught. Okay, we're going to reject H naught because the the z the test statistics is greater than the critical. The test statistics is greater than the critical z-score, which is given as 326 here. Right. So I hope that is clear. Now that is our main decision. Now, in order to conclude based on the context itself, even though the context in this question was quite standard, therefore the conclusion is always best to write down the conclusion in such a way, saying that conclusion. Okay, what are we testing here? We want to check whether we want to test whether the population mean of B is greater than population A or not. But since we rejected the null hypothesis, therefore the alternative hypothesis should be true. Therefore, we say that yes, the population mean for B indeed is we have sufficient evidence to suggest that this population mean for B is actually greater than the population mean of A. So therefore, here we can say that we have sufficient evidence or significant evidence to suggest that the population's mean for B is indeed greater than the population mean for A. Right. So I hope that is clear for the first sections here. Right. Okay. Okay, you can check through. All right. So don't forget in the exam, after you write down the decision here, always write a formal conclusion based on the context of the storyline, right? Okay. Now next, we're going to complete the last sections of this question here. Right. Now we don't need all this anymore. Okay. Okay. All right. Now let's read through what we have for this section here. Now this is the width of an um, alpha significant or alpha percentage of confidence interval for the difference between the mean population is found to be 1.82. Therefore, we are asked to find the value for this significant level alpha. Right? Sorry, not significant level. I think I made a mistake here. The width of the confidence interval. Right? Now, just to show you how the confidence interval look like initially, it actually looks something like this. Okay, write it down one more time. Okay, so the confidence interval is given by y. Oops, I should have write down plus. Supposed to be subtract minus z score and then multiply by the standards of error. And then this side also the same. Alright, so there you have it. Now, what do they mean by the width of the confidence interval? So the width of CI, I just label it as W, is actually given by the difference between the upper bound and the lower bound. So if you actually take this, subtract with this, you indirectly we cancel off the difference between the mean itself. We will get 2z standards or error. Alright, so there you have it. And then we are given that the width is 1.82, or we can actually write down this as 0.91. Okay, and then we have calculated our standard or error previously. It was this, so therefore we can actually calculate our z-score in this case by taking 0.19 divided by 0.513 or 5128, if I still recall correctly just now. Right? And then from here, right, your z-score that you will get, let me check. If I'm not mistaken, it will be based on my calculations. It should be, I just round it up to three significant figures here, 1.77. You should get 1.77 here. Right? Okay. And then what does that actually mean? Okay. Now I'm going to erase off this. Oops. Let me get this clear. So what do we mean by 1.77 z-score here, right? So let's look at the distributions here. All right. Now 1.77, it should be somewhere here. This is 1.77 here, right? And then the width would be between here 1.77 to negative 1.77. All right. And then we need to find the uh, area in between negative 1.77 and 1.77, basically. Right. Now, of course, there are advanced calculator that you can use that can help you to calculate directly. But due to the exam purpose. So you have to refer to your MF19 itself. So to refer to MF19, now your MF19 will give you this shaded region, which means it will give you this area. It will give us this area. But what we need is in between there. So what should we do with this? We're going to take this area. Okay, we're going to take this area, and then we're going to use this to figure out this section here. Okay, this section, right? So therefore, um, this area here, let's try to refer to the data booklet here. For simplification, um, I just call this now there's a formal notations for this. Usually they label this as uh, 1.77. Okay, so this blue region is labeled as phi 1.77 in this case, right? And then all I need to do is, in order to find the red area here, so the red region, therefore I can say that the percentage of the confidence interval would be given by, I can take 100%, of course. Okay, subtract off with this one here. So if I subtract off with this, what I get is actually this region here, this region. But I need to get in between here. So what I need to do is, now there are two areas here, so therefore I can actually take this one. Oops, let me rewrite that properly. So therefore this area here is given by 1 minus phi 1.77. Okay, I hope that's clear. And then now this section here, this section is also 1 minus phi 1.77. All right. So those two regions. And then what we need is in between there. So to get the area in between, we're going to take 1 minus of 2. Okay, and then if you try to simplify that, we will get 2 phi 1.77 minus 1 here. Okay, and then of course you need to refer to your MF19 for the z-score. All right, let me refer back to my MF19 one more time. Okay, where is that MF19? Hold up, it's missing already. Yep, okay. So let's look at this MF19 here. We need to look for the z-score 1.77. So if you look at 1.7, 1, 2, 3, 4, 5, 6, 7. So 1.77 is somewhere here. So 1.7, 1, 2, 3, 4, 5, 6, 7. So 1.77 is over here. This one is 0.9616. 0.9616. All right, so we're going to take this multiply by 0.9616, and then after that we're going to subtract by 1. Okay, so just let me clean this up so that it's not too messy. All right, so this is how it look like. Right, and then there you have it. If you try to simplify this, you will get, oh yeah, I forgot that this is supposed to be in percentage, so therefore don't forget at the end you have to multiply by 100%. Yep, I just put a percentage symbol here. Here you have to multiply by 100%. So if you take this multiplied by 100%, you should end up with, I have already done the calculation again. That should be 92.4%. Okay, so I hope that is clear for this question. Right. Stay tuned for the next one. All right, let's look at our second question here. We have metal rods produced by certain factory claimed to have median breaking strength of 200 tons in this case. Now, for a random sample of 9 rods, the breaking strength measured in tons were as follows. So we have how many sets of data do we have here? We have 9 sets of data corresponding to the 9 rods there. Now, scientists believes that median breaking strength of metal rods produced by this factory is less than 200 tons. Right? Now, we're going to use a Wilcoxon sign rank test at 5% significant level to test whether there is evidence to support the scientists' belief. All right. Now, I hope that is clear. Right. Now, before we proceed further here, every time you deal with hypothesis testing, it's always good to look at what are we testing in this case. All right. So if you read that again, it says that to test whether there is evidence to support the scientists' belief that the rods produced by this factory is less than 200 tons. So therefore, this part here will be our alternative hypothesis. Right? Therefore, we're going to write down our statements of hypothesis first before we proceed on. Therefore, our null hypothesis, we're going to write down, let's call this median. All right, so median M is equal to 200 tons. All right. It's just my habit of writing the units there, but I believe that in the exam they should be fine with units. But it's always good to put in the units there because it does make a difference, right? If it come with the different units later, right? Now the alternative, we have already identified the alternative hypothesis from these statements here. Now the alternative hypothesis should state that since I call this median, so the median would be less than 200 tons. All right, and then there you have it. We have successfully set up our statements of hypothesis. All right, now what next if we want to carry out Wilcoxon sign rank test? Right? The next step is to construct a table to encapsulate all the informations for the sample that we have collected here, right? So I'm going to show you that here. Now the table itself. All right, so we need to have a table constructed. That depends on your style. It's not compulsory things to do here, but it's always good to have a systematic way to record the result so that we will make less mistake here. All right, so from here itself, we're going to list down all the strength of the rods itself. Now we are going to compare that with the median. Okay, we're going to calculate the difference between the strength of each individual rod with the median itself. So therefore, the first one would be a 10. Now, usually in the exam, we're going to do it manually in this case. All right, so that will be like negative 14, negative 12, and then this is at 8, negative 16. Assume that's negative 16, and then negative 9, and then you have like 15, you have negative 2, and then you have negative 4. All right, and then there you have it. This is the difference between each individual strength of the rod compared to the median itself. Right. And then next, we're going to calculate the absolute value for this difference. So the absolute value for this would be quite straightforward. All we need to do is convert the negative to positive, and positive will remain as positive. All right, and then there you have it. Those are the magnitude. Why do we need the absolute value here? It's because we need to um, create the ranking for each one of these strength of the rod. Right? So based on this, now usually in the exam we have to do it manually, so no choice. Well, if you can use computer, it can actually help you to auto rank for us. Right? So let's assume that I rank this correctly. Hopefully I rank this correctly. So we have rank number 1 here, and then after that it's quite obvious. We have rank 2 here, and then thereafter we have like 3, 4, okay, and then a 5, and then thereafter we have a 6, 7 here, and then 8, and then finally we have 9 there. So we should have 9 ranking because we have 9 roads here, right? Always try to check through if you got everything's correct. So if you are happy with this, then the next thing to do from here would be quite straightforward. So I'm going to produce the sum of ranks that represent the positive difference. Positive difference. So positive difference would refer to this one here. I'll make a marking. So this is positive difference. We have a positive difference here. The difference is positive. Bear in mind, not referring to the magnitude, referring to the original difference. So from here, um, okay, now from here, our P, I just use P to represent the uh, sum of positive ranking, right? Sum of ranks that represent the difference for the positive value, right? The positive difference in this case, right? So the P in this case would be based on this, we are going to have the sum of rank for all the positive differences. There will be 5, 3, and 8. So from here, we will have 16 here. Right. And then thereafter also, don't forget to create the sum of rank that represent the negative differences. Okay, so the negative differences will be here. I'm going to put a different color here. 7, 6. All right, now I'm going to sum it up directly. So we have 13 here, 22, 26, 27 of course, 29 here. So therefore, we have 29. So therefore, I'm going to rewrite that one more time. We have 9 plus 4 plus 1 plus 2. We have 29 here. All right. Now, you can always check in this case, all right, to see whether we have summed up the all the ranks correctly. So for checking purpose, okay, at this point, for checking purpose, before we proceed on, we know that P plus Q is equal to 45. Okay. Now, there is a way to check whether we got this correctly up to a certain extent, of course. We can always use that formula, sum of all the rank in this case. That is given by this. The first, you can say that the first number, here I'm going to use A and L, then it'll be easier. The first number and the last number, we are looking at the arithmetics progression here. Right, now we have 9 sets of rod, 9 sets of data. Our first one must be ranked number 1, of course. Our last rank must be a 9 then. Okay. And then therefore, in this case, you get 45, which tally very nicely with P plus Q. So therefore, I have a certain confidence for myself, knowing that I have tabulated the sum of rank for the positive and negative differences correctly. All right. Okay. I hope that's clear. Always check because human being bounds to make mistake. All right. Now, once you are satisfied with this, okay. Now I don't really need this anymore. I'm going to erase this. Now I'm going to summarize my test statistics. So therefore, my test statistics. So for my test statistics itself, I need to choose based on the data booklet or MF19. All right. Now I'm going to write this one down based on the value that we have already seen from the MF19 just now. Right. Now the T value need to be the smaller value between P and Q. So the smaller value between this is 16 here. All right, now there you have it. That will be our test statistics. Always take the smaller value between P and Q, based on the instructions given in the MF19. All right. All right. So if you can't remember how to carry out Wilcoxon sign rank test in this case, you can always come back to your MF19 here. Now, in this MF19, they give you the instructions like how do you actually carry out the sign rank test in this case. Right? So if you look at the instructions given, the sample size has size n in this case. P is the sum of the ranks corresponding to the positive differences. We did see that in our calculation just now. We have a set of sum or positive rank. We can label that as P. And then we also have Q, which is the sum of ranks corresponding to the negative differences. Right? Now from here onwards, right, the next instruction is very important. Right, we're going to choose the T, which is known as our test statistics. Between this P and Q, we're going to choose the smallest. Uh, I would say the smaller value between the P and Q to represent our test statistics T here. Now, once you have done that, okay, we're going to scroll down further and then refer to the critical value of T here. Okay, so there are a few sections here. We look at the since we are performing one tail test, okay, and then we are going to look at the sample size in this case. All right, we are looking at 9 in this case. All right, we have a 9 sample size 9. And then next, the significant level is a one tail test. So significant level is 5% in this case. All right. So therefore, I'm going to choose this 5%. So this is 5%. The sample size is 9. And then one tail test. Therefore, the critical values of T in this case is 8. All right, now we're going to bring this value back to our calculations and we're going to compare this critical value of T with the smaller value between the sum of rank between the positive differences and the negative differences. Yeah. Then we're going to make our conclusions accordingly. Right. Now, the other thing before I flip back to our calculation, now for each value of n, the table gives the largest value of t, which will lead to rejection of the null hypothesis at the level of significant indicated. So what that means is, if your test statistics value t is actually less than this largest value of t from this table itself, less than the critical value of t from this table itself, then we have sufficient evidence to reject the null hypothesis. That is what it meant by that particular instructions there. All right. So I hope that is clear. We're going to come back to our calculations. We're going to resume from there. Okay. Now once we got this, okay. Now the next one is just visual perceptions that I want you to have whenever you answer a sign rank test question. So assuming that, all right, even though this is a non-parametric test, there is no normal distributions here, but I'm going to use that shape as a reference only. So let's assume that we have some sorts of distributions like this. And then from the data booklet just now, MF19, we found that the critical value, the critical value is an 8. Critical value is an 8. So I just roughly write this one down as okay, assuming that the axis start from there. So the 8 is somewhere here. So this is the critical value 8 that we have obtained from the data booklet. But our test statistics suggest that it is 16 here. This section is called the rejection zone. Therefore, we are looking at whether our test statistics actually fall in the rejection region or not. If it is actually in the rejection region, then we are going to reject our null hypothesis. But we know very clear here because t here, which is equal to 16, is much more greater than the critical, the t critical, which is an 8 here. Therefore, we don't have sufficient evidence to reject the null hypothesis, right? So we have to accept the null hypothesis in this case, right? So no sufficient or no significant evidence to reject H naught. If you don't have evidence to reject H naught, we just have to accept the H naught in this case. Therefore, yes, the therefore we have to conclude it. Okay, don't just stop here. So the conclusions will be, in this case, I'm going to write down the conclusions part. So the conclusions here, uh, does is there any evidence to support the scientist's belief? All right. So therefore, no, there is no significant evidence to support the scientist's belief. Right? No evidence. Here, I just make it short. In the exam, you can write down no significant evidence to support the scientist's belief. And then what is their belief? Their belief that the median is less than. So in this case, I write it down here, 200 tons. And then there you have it. All right, that is the complete test to verify whether there is evidence to support the scientist's belief or not. All right, so I hope that is clear. We're going to move on to the second section shortly. All right, sections B for this question here. We need to give a reason as to why a Wilcoxon sign rank test is preferable to a sign test when both are valid. Yeah, of course, when both are valid in this case. Right. Now I'm going to give you a few pointers as to why, in this case, Wilcoxon sign rank test is more preferable as compared to the normal sign test itself. Right. Now, first of all, the similarity between Wilcoxon sign rank test and the normal sign rank sign test, sorry, not sign rank test, the normal sign test is this one here. All right. So both of them are non-parametric tools for carrying out hypothesis testing. Now, both of them incorporate or calculate the difference for each individual data as compared to its median. Yeah, so both of them use that data for evaluation, right? But what is the difference here? So the main difference between Wilcoxon sign rank test and the normal sign test is this one here. Right? Now, Wilcoxon sign rank test take into account magnitude of the difference that both of them has already calculated. And then next, it uses this absolute difference to construct the ranking. So that is the main reason as to why the sign rank test for Wilcoxon is more preferable in this case, because we can construct the ranking and then using the absolute difference here. Right? Now I hope that is clear. We're going to move on to the third questions shortly. All right, let's take a look at our third question here regarding chi-square test. Right? So apples are sold in bags of five. Based on her previous experience, Freya claims that the probability of any apple weighing more than 100 grams is 0.35, independently of other apples in the bag. Right. Now, the apples in the random sample of 150 bags are checked, and the number X in each bag weighing more than 100 grams is recorded. Now, the results are shown in the following table there. Now, we need to carry out a goodness of fit, which indirectly means chi-square test at 5% significant level, and then hence we need to provide a conclusion to Freya's claim in this case, right? Okay. Right. Now, as usual, before we can carry out the hypothesis test, we must write down the statements of hypothesis here. Right? For goodness of fit, usually the statement is pretty standard. So in this case, I'm going to write that down first. The null hypothesis, we want to test whether this is a good fit or not, right? So let's take a look here. Um, Now, Freya claims that the probability of any apples weighing more than 100 grams is 0.35, independently of other apples in the bag itself. All right. Now, the word independently indirectly gives us an idea. It is a binomial distribution in this case. We have number of trials, which is 5, probability of success of 0.35 here. All right. Okay, so therefore, our null hypothesis would state that uh, the binomial, I would say that binomial distribution, or I just, okay, before I write this, I would write down let x. Now let x represent the numbers of apples. Right? So here, number weighing more than 100 gram, right? Weighing more than 100 grams here, right? And then for this, we can represent the x is binomial distributions with number of trials to be 5, and then probability distributions or probability of success is 0.35 here, right? So let's state our null hypothesis. We will say that this binomial distribution is a good fit to the above data. All right, it'll be a good fit. Of course, if you like to ignore the alternative hypothesis, you can do so, because generally the alternative hypothesis is just the uh, opposite, right? So we can say that just for formality, I'll write it down as this is not a good fit. All right, and then there you have it. That is our statements or hypothesis. All right. Now, of course, in the exam, do we really need to write very formally like this? You don't really have to. It's just my habit. I just want to make it clear as to what we are representing for x here, right? Okay, so once you are done with this, as usual, in order to carry out the chi-square test, we need to construct a table. It's always good to construct a table. Let me bring you up the table here. Okay, hold on. Let me see. Where is my table here? Okay. This is the table that we're going to use for tabulating all the data that we have been given here. All right. Let me erase off some of this. Okay. All right. Now, in this table here, we have the x, which is the discrete value that represent number of apples in the bag itself. Okay, in one bag especially. The observed frequency is given, so you can see that the observed frequency is 12, 39, 46, 37, 12, 14 here. Right. These are all given here. And then next, we need to determine the individual probability based on the model that we wish to use here, right? Okay. Now, before I continue further, let me erase off this. Let me just rewrite on top here. Okay. So just for reference, we have um, is a good fit. Right now for the above data. Here I skip the alternative hypothesis here. Okay, now the first part we are going to calculate the probability of getting no apples that weigh more than 100 gram here. To do that, we know that our binomial distribution is given as such. Okay, all we need to do is calculate x equal to 0. That will be given by, um, let me see here, 5, 0, and then a probability of failure. Okay, so if you actually key this one into your calculator here, you would be able to get, okay, just let me try this out. 5C0 is a 1, 0.35 to about 0 is a 1, and then therefore, hold on, 0.65 to about 5 there. All right. So from here, you would be able to get 0.116029 there. Okay. All right. So here we're going to fill this up, 0.116029. Right. Now next we're going to obtain the expected frequency based on our model. So the first expected frequency based on x equal to 0 will be given by n p x equal to 0 here. And then the n, in this case, the n is not this n here. This is number of trials. The n that we are referring to is the sample size. Yeah, it's the sample size in this case, right? Now, if you forgot what is sample size given in the previous question, we can always sum this up here. Okay, let's assume that I have forgotten, so I'm going to sum this up here. Just give me a while. 7. Okay, so total is 150 here. You can also get the n from the table itself, right? So that's the advantage of constructing the table itself, right? So from here we can take 150 by, right? Or you can use every single decimal in your calculator itself. Roughly you would get, let me see, what do you get here? Mm, Okay, let's assume that I use up to 29 by 150. So I should get 17.404. So if you like, you leave it as 3 decimal places here. That is fine. And then thereafter, we're going to calculate the first individual chi-square value, which is given by this. Okay, now that would be a 12, 4, sorry. So that is 404 square divided by, okay. So from here itself, I'm going to try to calculate this. Okay, let me see here. We have 17 point. So 17.404. All right, and then after that, okay, and then you divide by 17 point. All right, so here you will get the first chi-square to be like 1.678, for instance. All right, and then there you go. That's the first chi-square value. And then of course you can proceed on with the second one, and so on and so forth, right? Okay, now stay tuned. I'm going to show you all the numbers that I have already pre-tabulated to speed up the process here, right? So stay. All right, here you are, all the tabulated value for the observed frequency and the expected frequency, including the individual chi-square calculations. Right. Now, next we're going to tabulate the test statistics by summing up all the individual chi-square values here. That would actually give us this. Okay, we have sets of data from okay, from 1 until okay, we have 1 until 5 here, right? Okay, so we can actually sum up all these numbers here. Okay, now let me sum them up. Okay, so therefore we have 1.678, 1.318, and then we have 10.310, and then finally we have 13. Oops. Okay, we have 13.097. All right, and then there you have it. So if you tabulate using your calculator, you will end up with, I have already pre-calculated this, 353. Okay, something wrong with my pen here. Okay, um, 353 there, right? Now you will notice that I have committed a major mistake whenever I carry out my chi-square test. So if you knew the mistake, well done, right? If you can't remember, okay, this is a reminder, right? Always check your expected frequency, and sometimes you might want to check your observed frequency also. If there's anything that is less than 5, less than 5, we don't say high five. If you get more than 5, equal to 5 or more than 5, yes, we say high five. All right. So here we notice that one of our expected frequency is less than 5. Because of this condition, we have to rectify the calculations of our chi-square here. So at this point, I need to make a remark. Bear in mind, this is not the correct calculation, right? So please remind yourself to check uh, the expected frequency for any individual expected frequency that might be less than 5 here. So one of them is here. Because one of them is less than 5, therefore you have to combine few rows together to ensure that the expected frequency is more than 5. So here we can combine row number 4 and row number 5 here. Right? So if we combine these two, we will be able to obtain expected frequency that is more than 5 here. All right. So here I'm going to combine these two. I'm going to show you the new combined table, and then we're going to retabulate the test statistics. All right. So we have reminded ourselves of the errors or the precautions that you need to take whenever you are answering questions involving hypothesis tests using chi-square, right? Always check the expected frequency whether it's greater than 5 or not, right? So here I have already combined row 4 and 5 together. So by combining, I'm combining the observed frequency, don't forget. You must also combine the expected frequency, and then at the same time we have to recalculate, bear in mind, recalculate the individual chi-square here. Now this time we're going to sum all this up here, okay, using the same formula. Okay, so we will rewrite this one more time. Okay, and then I'm going to sum up all this number here. All right, I have already pre-calculated this to speed up the time here. So we have 641 here. Right. Now that will be our correct test statistics chi-square value. All right. Now I hope that is clear. Now from here onward, we are going to refer to our MF19 and then obtain the critical value at 5% significant level for the chi-square. Right. So I'm going to open my MF19 now. All right, here is our data booklet MF19. We are going to refer under the chi-square distributions section. Okay, now there are a few informations that you need to remember before you can obtain the critical chi-square value. So first of all is the degree of freedom. Now we know that we have already combined two rows together. Previously, there is six rows, so we combine two of them, right? So now we have five. Okay, so we have five in this case. So therefore, our degree of freedom, so don't forget our degree of freedom is n minus 1 now. Since the number of rows that we have is 5, so we'll take 5 minus 1, which is equal to a 4. So our degree of freedom is 4. Look under 4 there. At 5% significant level. So 5% means the rejection region is 5% here. Therefore, we are supposed to look for 95% in this data booklet. So if we look through this, we will get 9.488. Okay, we're going to extract this critical chi-square value and then put it back to our previous calculation. Right? All right, we are back here now. Since after we have referred to the MF19 just now, so from MF19, our critical, here I just write down, from MF19, we found that our critical chi-square value is 9.488. All right, so by using this, we're going to compare this critical value with our test statistics and then make our conclusions accordingly. All right. And then our null hypothesis is still here, just for reference. Okay. Now from here, we are going to I'm going to sketch the graph again just to show you what we are looking at. Okay. So in this case, this is a chi-square curve, just a rough sketch. So we have our critical value as somewhere here. This is 9.488. Okay, and then our test statistics that we have is here, which is 14.64. All right. Okay, 14.64. All right. Okay, since the test statistics actually fall in the rejection region, so this is rejection region. All right, now since our test statistics fall in the rejection region, therefore we have sufficient or significant evidence to reject our null hypothesis. So we're going to reject our H naught, right? Because the main reason is because our chi-square is greater than the critical value. All right, so I hope that is clear at this point. So we also need to comment on Freya's claim in this case. So Freya's claims that this is a good fit. So since we rejected this, therefore we will conclude that the binomial distribution is not a good fit. Right? So that will be the conclusions for this question here. I hope that is clear. We're going to proceed on to the next question shortly. All right, question 4 here. So we have members of sprint athletes club have been taking place has been taking part in an intense training scheme aimed at reducing their times taken to run 400 meters. For a random sample of 9 athletes from the club, the times taken in seconds before and after the training scheme are given in the following table. So the organizer of the training scheme claims that on average, an athlete time will be reduced by at least 0.3 seconds. So we need to carry out a test at 10 percent significant level, whether the organizer's claim is justified, stating any assumptions that you make in this case, right? Okay, now for this question, as usual, um, we need to find the difference first, and then construct a table to tabulate all the necessary calculations that we need to complete this hypothesis testing, right? Okay, I'm going to show you the next sections here before we continue. All right, now the table that we need will be here. Right, we need to tabulate its difference between the sample that we have collected regarding the time to complete the race itself. Okay, before and after. All right. Okay. Now from here, as usual, we need to write down the statements or hypothesis. So we're going to, maybe I'm going to label this as the population mean is represented as 1 here, and then this is 2 to represent the population's mean after the training itself. Right? Therefore, our hypothesis testing statements would be, our null hypothesis would be, the difference should be 0.3. Okay, there's always something wrong with my writing here. Sorry about that. Okay, so 0.3. And then the alternative hypothesis, you have already seen that in the statement itself. We want to carry out a hypothesis test to check whether there is an improvement due to the training itself. So therefore, we are testing whether there is a difference of at least 0.3. So that is what we are trying to test here. At least 0.3 second here, just to make it clear. All right. Now, sometimes you can also use um, the different notations to write your hypothesis statement. Since we use D to represent the difference here, so we can also represent this as D is equal to 0.3, or we can write down our alternative hypothesis as D greater than 0.3. All right, so I hope that's clear. Right, next we're going to tabulate all these differences and their square, and then thereafter we're going to determine the mean and the variance for their differences. Okay, let's start it with the difference first. So here we get 0.9, 0.81. Okay, and then here you get 0.4, I believe. Okay, 0.16, and then you have 0.7. Okay, so from here you have 0.5, and then here you get a negative 0.2, and then thereafter you have 0. Okay, after that you have this is negative 0.1, 1 here, and then after that you have what do we have here? You have 1.2, 1.44, and then finally you have 0.3. Okay, so from here we can tabulate all the sum here. Just let me check one more time before we continue. Okay, so we do have the sum that is required here. So if we sum all this up, we will get 3.7 here. So this is the sum of all the differences. And then if you sum up the square of them, okay, just let me try out one more time. Okay, so I will get the sum of the square of their difference. That is 3.29. Okay, so next I'm going to make use of all this result here to compute the mean for the differences, which is given as divided by n in this case. Okay. Now the n that we are looking at is 9 sets of data. So this is 9 here, just for reference. So from here we have 3.7 divided by 9. That will be right 0.411 here. All right. And then next we're going to calculate variance, the variance of their difference. Now, here I just write down the number directly. So it's just 3.29. Subtract off with the sum. 8. So I'm using the unbiased calculations for the variance itself. So if you tabulate this, you should end up with 0.2211. Okay, so I hope that is clear. And then next we're going to proceed on to carry out the test statistics. And then we get to calculate the t-test test statistics value here, which is given by this divided by okay. And then from here we are going to write down 0.411 divided by whatever numbers that we have just now, divided by 9. Alright, so if I were to tabulate this, okay, just let me try this out here. To 0. Okay, so I will end up with 0.708 in this case, right? So I hope that's clear. Now next, we're going to refer to our MF 19 again, and then we're going to look for 10% significant level. So 10% significant level um, for one tail test in this case, we are supposed to look for 90%. So don't forget, look for 90%. We're going to find the critical value for our test. All right, here we are. We're going to refer to the t distributions here. Okay, and then don't forget we have degree of freedom given by n minus 1. The sample size that we have just now was 9, so 9 minus 1 is 8 in this case, right? So our degree of freedom will be 8. We're going to look under this. And then we know that we are carrying out a hypothesis test at 10%. So our rejection region is 10%. We are supposed to look for uh, 90%. Okay, 90%. Okay, that is so this is 10% rejection region. One tail test in this case. So we are supposed to look for 90%. 90% would actually give us this. So 1.397. 1.397. Therefore, we want to compare this critical t value with our test statistics. Therefore, we can make a conclusion shortly. All right, we're going to go back to our previous question. All right, once we have referred to the MF19 just now, we found that our critical t value, the critical t value, I just write down a C here, from the data booklet was 397 here. As you can see, this value here is way larger than 0.708. Therefore, this test statistics does not fall in the rejection zone. Therefore, we're going to accept our null hypothesis. Therefore, reject the alternative hypothesis here. As a conclusion, we're going to, in this case, we're going to say that we're going to accept, or we have sufficient or significant evidence to suggest that we can accept the null hypothesis. And then therefore we need to provide comment also, all right, to check whether the difference is at least 0.3. So because we have accepted the null hypothesis, so therefore we have insufficient evidence to support the claim. In this case, you can actually say that we have insufficient evidence to support the claims that the difference is at least 0.3 second. Right? So I hope that is clear. We can move on to question 5 shortly. Question 5, we have Kara has two unbiased coins. She tosses both coins. The number of heads obtained by Kara is denoted by X. So we need to find the probability generating functions with respect to T in this case, right? Of the discrete random variable X here. Right? Okay. Now, unbiased coin basically refer to probability of getting a head is half. Probability of getting a tail is also a half. So she has the two unbiased coins. So flip at the same time. Then we are going to tabulate the probability there, right? Now, of course, it's always best if we can get a form of table to record this, right? So let's take a look. All right, this is how the table would look like. Okay. Now there are many ways to obtain the probability of not getting any head, getting one head, or getting no two heads, and so on. Right? So I think that sometimes the easy way is by using tree diagram if you are a visual person like me. So you have the first coin, and then you have the second coin. All right, so the first coin you can either get a head or a tail, of course. All right, now the chances is half here, and then the same thing go for the second one. Is either you get a head or a tail. or a head or a tail here. Now all the probability is the same. It's a half. All right. Let's observe all the outcomes that we can expect to get from here. So you can either get a head or HT, TH, or TT here. All right. Now to obtain the probability of not getting ahead, you can only see that the only outcomes that show not getting ahead is just one out of four here. So therefore, the easiest way is to just write one out of four in this case. All right. Okay, so we'll write down one out of four. All right. And then the probability of getting ahead, you can see that there are two outcomes out of four. So I just write down two out of four here. And then lastly, getting two heads, there's only one outcome out of four. And then it's always good to check because this is a discrete random variable. So you might want to check the sum of its probability must be equal to a 1 here. So let's do a quick check. Yes, it does sum up to 1. So the sum of this, yep, is equal to 1 here. Okay, now we are all good. Once we have tabulated all the discrete random variable with its corresponding probability, now it's time for us to set up or write down the probability generating function uh, for random variable x, right? So we don't need this anymore. Let's just clean this up. Now, therefore, the probability generating functions p, I just write down in short, of x here, which is given as gxt. Now, some of you which is a fan of the formula for probability generating functions, and the formula is given by, all right, so that is the probability generating functions here. And then all we need to do is just substitute all the corresponding probability into this. So we'll start from where should we start first? Okay, so we can start from 0. So 0 means t to the power of 0, and then corresponding to its probability here. So 1 over 4. And then thereafter we have t, 2 over 4. And then after that t2, 1 over 4 here. Okay, from here, if you like to rearrange it properly, we will get 1 quarter 2 4t plus 1 quarter t square. Some of you like to simplify it. Yes, you can go ahead. Right? That is it's of your choice. Now there you have it. That is what we call as the probability generating functions of x here. All right. Now I'm going to move on to the second part shortly. Right. As for the second part, this is a different person now. Hassan has three coins, two of which are biased. So the probability of obtaining a head when the coin is tossed is 1/3. The corresponding probability for the third coin is 1 quarter. The number of heads obtained by Hassan when he tosses these three coins is denoted by y. Right? So we need to find the probability generating functions gy of t. Okay, now as usual, we need a table to construct this result here. And then this time the coins sort of biased, two of which are biased, so that the probability of obtaining a head when the coin is tossed is 1/3. And then the corresponding probability for the third is 1 quarter there. All right, so let's check this out. The same thing, we're going to employ a tree diagram. So we have three coins here. So here I'm going to write down the first one. Then you have the second one, second coin, and then thereafter you have the third one. Okay, right. And then we have either a head or a tail. Okay, two of which are biased. So let's assume that the first one is biased. So the probability of getting a head is 1/3, and then probability of getting a tail must be 2/3 then. Okay, and then next one we have the second part here. Also getting a head and tail. Same thing go here. Also head and tail. So let's assume that the second coin is also biased. So therefore it means this is also 1/3. This is 2/3. This is 1/3. This one will be 2/3. Alright. And then lastly, the third coin. The corresponding probability for the third coin is 1/4. What it meant is the probability of getting a head for the third coin is 1/4. So also get a head and a tail. The same go for here. And then next we have it here. And then lastly we have it over here. Alright. And then the probability will be very different at this point. Okay, so this one will be like 1/4, and then this one will be 3/4, 1/4, 3/4 here. All right. And then thereafter, our outcomes. All right, our outcomes, we will have like, of course, we will have three heads here. Or you could have HHT and so on and so forth. Okay, I'll write down everything. Okay. Now, once we have done that, we're going to calculate each individual probability because each one of them has a different probability here. Now, the first one, not getting any head at all. So, not getting any head, that's the only one here. The probability will be this multiplied with this and this. So, we have like 36 over 36. You have like 12 over 36. All right, now that's the first one. And then after that, I'm going to go with the last one because the last one is the easiest one. When we have three heads all together, that will be here. And then that would actually give me like 1 out of 36. Very obvious. So this one is 1 out of 36. Okay, cool. And then after that, the toughest one is to determine one head and two heads in this case. So one head, let's look at one head. I have it here, here, and here. All right, let's tabulate this one here, this branch. So this branch gives us a 6 over 36. And then this branch here, which branch is that? So that is also 6, 36. And then the last one is TTH. So that is like a 4 out of 36. Okay, and then that would actually give us a 16 out of 36. All right. And then lastly, I also like to tabulate this one just to check. We have what we have here. We have 3 out of 36, and then HTH is 2 out of 36, and then thereafter we have THH, that is 2 out of 36. All right, so from here I will get like 7. So 7 out of 36. And then of course it's always best to check whether the sum of the probability is equal to 1 or not. If it's equal to 1, then I have successfully obtained all its probability for the corresponding discrete random variable. Right? So let me see here, what do we have? We have 8, 24, 36, yes. So the sum is indeed equal to 1. Therefore, I have successfully constructed the um, probability distributions table. All right. Now, once you have done this, the next step is pretty much simple. All you need to do is just clean this up first. So from here onwards, the probability generating functions for y can be written as the same formula here. Okay, now since this is a y, okay, maybe I'll change the notations a bit. I'll say this is a y. Okay, even though here I'm using x, but doesn't matter. It's just a general notation. All right. So from here, I will start off from t0, 1236. There's always something wrong with my tree. Okay, hold on. Okay, 36, and then thereafter I will have t 16 over 36, and then after that I have t square 6, and then finally I have t cube 1 over 36. So thereafter I'm going to arrange this neatly, so that will be 12 over 36. And then there you have it. That is the probability generating functions for y in this case, right? So I hope that is clear at this point. Okay. Now in terms of notations, yeah, some of you might want to be more strict in this case, since we are dealing with a random variable y. You might want to change this to y equal to y. That should be fine. All right. So I'm going to proceed on to question C shortly. All right, so let's take a look at question C here. I just copied down our previous probability generating function for x and y here for reference. Okay. Um, Now, there is another random variable z that represents the total number of heads obtained by both Kira and Hassan. So we need to find the probability generating function of z that represent the sum of number of heads obtained by both of these person. Right? So there is now since both of the probability are independent, both of the events are independent. Therefore, now before that, we are going to write down whatever z, the random variable z actually represent. So random variable z actually represent the sum of both of these random variable, and then the probability generating function for z can be written as the products of the probability generating function for x and probability generating functions for y. Right. Only if both of the events are independent to each other, right? So from here, we're going to key in all this. And then multiply that with this. Okay. And then from here, we can sort of, oh yeah, this one I have already simplified that. If you don't want to simplify, you can keep it as, okay, I think it was 2 over 4 previously. So I just leave it as 2 over 4 here. Okay, so from here we can factorize everything. So to, for instance, I'll take out 144 then. Then that would actually give me a 1, 2t, t square, and then I'll have 12, 16t, 7t square, and then finally t cube. Right. And then of course you can expand this. Okay, if I were to expand this, let me see. Okay, what do I have here? I have a 12, 16t, okay, and then thereafter 24t, 32t square, and then 14t cube, t cube, yep, correct, and then 2t4, and then after that I will have 12t square, 16t cube, and then 7t4, and then finally I have my t5 there. Okay, and then by simplifying the like terms, okay, let's see what do we have. I think we only have 12 here, and then for the t, we have 1 here, 1 here, anything else, no more, so therefore this one would yield 40t, and then for the square, so I have 1 square here, 2, 3. So that would actually give me like what, 44, 51. Did I get that right? Yep, correct, 51. So plus 51 t square, and then after that I will have my t cube. So 1, 2 here, and 3 here. So therefore I will have like 30, 31. Okay, so I will have 31 t cube, and then after that for my So this part here I'm done basically. So T4 I have a 9. So 9 T4. So 9 T4 here. And then finally I have my T5. And then there you have it. That will be my probability generating functions for Z here. All right. Now I hope that is clear at this point. I'm going to move on to the next section shortly. All right. This is our third questions here. We need to. Oops, we have already done our third question. Sorry here. I just rewrite our probability generating function for Z. Okay. We're going to move on to the next one of D here. Okay, there's a delay here. All right. Now we need to use the probability generating function Z to find our expected, to find our expected value for random variable Z here. All right. So to do that, there is a formula that we are going to use here. So the expected value of Z is actually given by the derivative of the probability generating functions of Z by substitute t equal to 1 here. All right. So this one has been derived in one of my videos there. I'll put a link up here, uh, up in this section here. So if you still want to look at how this formula was derived, you can refer to that. All right. Okay. So from here, we need to differentiate this. Okay, differentiate this probability generating function with respect to t in this case. All right. So if we do that, we have okay, we have 102 t 93 t square 36 is it 36? Yep, correct. 5 t4. All right. And then finally, in order to get the expected value for random variable z, is easy in this case by just substitute the value of t equal to 1 into the derivative. So if you substitute all this, you get 40. Okay, so let's see what do we have here. Um, okay, we have a big number here. We have 41. This one will be 195. So 41, 81 here. So therefore we get a 276. Okay, 276. Just let me check the number here. If I got it correct. Okay. Okay, there's a problem with my calculator. All right. Okay, let me try one more time here. All right, now that would yield approximately 1.92. Okay, let me see, 1.92 here. Now that would be the expected value for Z, right? Now I hope that is clear. We're going to move on to the last sections here. I'm going to just scroll directly. I'm going to leave the previous question here because the last section was quite direct. Okay, we can look at this. Okay, hold on. Okay, E. Use the probability generating function of Z, which we have it here, to find the most probable value of Z. What that actually means is what value of z that would actually produce the largest probability, the highest probability in this case, right? So let me erase off all this. We don't need this anymore. Okay. Now from here itself, right, you can see that the largest probability from this probability generating function is actually found here. So the largest probability is actually given by uh, the value when z is equal to 2. So when z is equal to 2, the probability is 51 over 144. And then this is the largest compared to the rest. Because of that, we have indirectly found the most probable value of z. So the most probable value of z is actually equal to 2 there. So the value of z is equal to 2, right? I hope that is clear at this point. I will move on to the last question shortly. Right, here come our last questions for this paper. Okay, let's look at this. This is a continuous random variable x has a cumulative distributions function f given as such. Now we need to find the interquartile range of x. Okay, now interquartile range basically refer to Q3. Q3 is the upper quartile, and then we need to subtract off with Q1, okay, which is the lower quartile in this case, right? Now, first of all, in order to find the upper quartile, okay, so upper quartile, something wrong with my pen. Okay, in order to find the upper quartile is given as this. Okay, hold on, just let me, to find the upper quartile, we need to solve this equation here. 0.75. So basically it means the cumulative frequency distributions must be equal to 75%. Right? That's how we find our upper quartile in this case. Okay, now from here, that will give us 16x. Okay, for me, I prefer to convert this into a fraction. 3 over 4 here, and then if you rearrange this, you would get plus 45. All right, and then of course here you need to use your calculator to solve this. Okay, right, now if I use my GeoGebra here, okay, I have already entered this. All right, so if you use your calculator to solve this, we will end up with two sets of answer. We can either get 3.64 or 12.36. All right, but we know that the domain for this cumulative frequency distribution is between 0 and 6. So therefore 12.36 has already exceeded the domain. Therefore, we can say that our upper quartile is actually given as 3.64 here. All right, so that will be our upper quartile, and then we're going to repeat the same using the same strategy here to obtain the Q1, which is our lower quartile. So our lower quartile would satisfy this equation of 0.25. All right, all we need to do is find the solutions to this equation, and then that solutions will be the lower quartile. And then in this case, if I substitute the same equations, I will end up with x squared plus 15. Okay, this one is easier to solve. You can see that is basically 15 and a 1 here. All right. Now, because of this, we are going to end up with 1 or 15. But because the domain is within 0 to 6, therefore our our lower quartile is given as 1 in this case. All right, so I hope that is clear at this point. Once we have found the upper quartile and lower quartile, we will be able to um, evaluate the interquartile range. So therefore, the IQR or interquartile range in this case is given as Q3 subtract off with Q1. We have 3.64 subtract off with 1. That would actually give us 2.64. All right. Now I hope that is clear for first section. We're going to move on to the second one shortly. All right. Second part of question 6 here. We need to find the expected value for EX3 here. Now before we can find this, we have to obtain its probability density functions from its cumulative distributions. Therefore, this probability density function is given by the derivative for the cumulative distribution function. And now here we will get, okay, now you have three piecewise function here, so we have to differentiate each one of these piecewise function. Now it's quite direct. You can see that when you differentiate 0 is a 0, when you differentiate 1 is a 0. Now the only thing left is to differentiate this function here for this domain. Right? So we have 160 and then you can simplify as all right, and then we are almost done. It's always best to describe fully these probability density functions for variable x. So therefore we're going to write as such. Oops, I shouldn't be using this one. I should be using the one that I have already simplified. Alright, now this one will be available for this domain, and then this one will be otherwise. Okay, now I hope that is clear. Once you have obtained the probability density functions, then we are ready to evaluate the expected value for x3 here. So the expected expression for this, right? Now that is basically given by x3 multiplied by fx. These are definitions for the expected function because this is the only domain that we have, so we're going to integrate that from within this domain itself. Okay, so from here we have 1 over 30 8x3, then subtract with x4 dx 0 to 6, and then from here let's see what do we have. Okay, and then from here, um, okay, let me clarify. When we find this expected value, we should expect to get a certain numerical values here, not the expected expression. Um, I try to correct my mistake there. Right. So all we need to do is just substitute this into our expression here. So 0 is definitely going to be 0. We have 6 to the power of 4, 6 to the power of 5. Okay, and then I'm going to use my GeoGebra here just to tabulate the final result so that it will be easier in this case. Okay, I will have this. So, and then if I want to leave it in terms of decimal, I should have 34.56. And then there you have it. That's my expected value for EX3 there. Now I hope that is clear. We're going to move on to the next question shortly. All right, here is our last questions for this question 6 here. Um, we have a random variable y is such that y is equal to square root of x. Okay, we're going to find the probability density function of y. To do that, what we are interested to find is this. Before that, we're going to find out the cumulative distributions for y, which is given by this. All right, and then we know that y is equal to the square root of x. So here I'm going to label that. Okay, and then next we can do a bit of manipulations here. That will give us x, which is less than square here. Right. Now we know that fx is actually given as this by definition. Now you can check out these two format here looks very similar. So therefore this is exactly the same as fy square to be precise, right? So to do that, all we need to do is just substitute this y square into the cumulative distributions function of x here, and then we will get um, 1 over 60, 16 y square minus y to the power of 4. All right, and then there you have it. This is our cumulative distribution function for y. But what we are interested to get is the probability density functions for y. Therefore, probability density functions for y is basically the derivative of the cumulative distributions of y in this case. So if we differentiate that, and then if you simplify it, let me see if you can simplify it by 4. I think you can simplify it by 4. Or you can write down as y over 15, 8 minus y square. And then to describe the density functions precisely, we will write down the probability density functions for y can be described as Okay, and then 0 otherwise. Now the only thing that we are left out with now is the domain, right? Now we know that the domain for x is here. Therefore, all we need to do is just substitute the lower bound and the upper bound here. Therefore, the y will range from 0 to square root of 6 there. So therefore, the domain for this will be, all right. Now that complete the probability density functions for y. All right. Now I hope this will be a useful revisions for you guys. I know that your exam is tomorrow. Okay, this is kind of a late revision for you guys. All the best again, since this is your last leg in your exam. Okay, best of luck, everyone. Until I see you guys again. Right?